It's my pleasure to welcome Nan to our webinar series at the Abruzzo Observatory. And I just want to spend a few words on Nan. Nan is a research assistant professor at Washington University in St. Louis. She obtained her PhD in 2014 in cosmochemistry from the University of Chicago. Her thesis focused on understanding the slow neutron capture process, the so-called S process, in asymptotic giant branch stars through isotopic analysis of a heavy element in micron-sized mainstream silicon carbide grains, using techniques as resonance ionization mass spectrometry. Then she spent 3 years working as a postdoc at the Department of Terrestrial Magnetism of the Carnegie Institute for Science. And finally, in 2018, she moved to Washington University in St. Louis. Nan's current research interests include understanding the origin and formation timing of presolar grain and associated AGB and supernova stellar nucleosynthesis, the analytical development on isotopic analysis on micron-sized samples, and the coordinated microanalysis using different techniques. So I guess you can start sharing the presentation, and you have 45 minutes. I will advise you when you 5 minutes are missing. Okay?
Okay.
Perfect.
Can you see my screen right now?
Yes, thanks.
All right. Thanks, Sergio, for the introduction and for having me here today. And ciao, everyone. My research, as Sergio said, focuses on asymptotic and structural analysis of presolar grains using a wide range of micro-analytic techniques. And today I will be talking to you about asymptotic giant branch stars and their dust grains in our solar system. As written in Carl Sagan's book, Cosmos, we are all made of star stuff. So it's good to know how we become what we are today by stellar nucleosynthesis and also galactic chemical evolution. So I know some of you are astronomers, so before the pandemic, I'm sure you can travel to such beautiful places to look at lights emitted by stars by using different telescopes. And we cosmochemists go to places like Antarctic to collect space rocks, meteorites. And it turns out most of the places that are good to build telescopes are also good places to collect meteorites. As we saw earlier, the La Silla Observatory is located on the outskirts of the Chilean Atacama Desert. And in fact, the Atacama Desert is also the home to one of the planet's most ancient collection of meteorites. So next time after the pandemic, if you can travel to the observatory, you may want to try meteorite hunting during the day just to look for black rocks. And, And or sometimes we don't even have to travel. We just wait for the meteorite to find us. So in 1969, so a 4.6 billion year old meteorite rained down a small farming town named Murchison. So it's a small town north of Melbourne in Australia. So the Gaelic brothers, Peter and Kim, aged at 10 and 11 at the time, became most dedicated to the meteorite search. So they quickly gained the reputation of knowing where to find such fragments of the meteorites. And they skipped many days of school, but as you can see here, they ended up with a large collection of the Murchison meteorites. And just to give you an idea, the current price of Murchison is around $1 per gram. And if you do the math, you can see this is really a big fortune. Also, as many of you know, so most of the stardust grains we study today were separated from Murchison. So if Murchison didn't fall at the time, so we wouldn't be where we are today for stardust grain research. Now you may wonder, so how these stellar dust grains ended up being buried in pristine meteorites in our own solar system. And this cartoon gives you a general picture. So the interstellar medium is a mixture of gas and dust lost from the surface of stars by stellar winds and also ejected by stellar explosions. And about 4.6 billion years ago, a molecular cloud in the interstellar medium collapsed to form our own solar system. And while the majority of the primordial dust grains got destroyed by heating and collisions in the early solar system, a very small fraction survived and got incorporated into planetesimals, which became asteroids and comets later. Some of the asteroids and comets did not experience any heating or collisions, and as a result, star dust grains are preserved in such pristine objects. Oops, wrong way. Then, due to frequent collisions between asteroids and constant dust jets from the surface of comets, some of their fragments got into Earth-crossing orbits and fall onto the Earth as meteorites and also interplanetary dust particles. So these primitive extraterrestrial materials brought us stardust grains on Earth essentially for free. And since these grains literally formed before the formation of our solar system, so we call them presolar grains. And before the discovery of presolar grains, our only approach to study stardust is by spectroscopic observations. And this is how stardust grains look like through telescopes. Shown here are the ALMA observations of supernova 1987A, and we clearly see the formation of dust grains in the center of the supernova remnant at shorter wavelengths. However, as many of you know, most dust phases have very weak spectral features and making it very challenging to study dust chemistry by spectroscopic observations. So where the telescope ends, the microscope begins. And to our cosmochemists, this is how the stellar dust grains look like under microscopes. So they have very different morphologies and also compositions, as you can see here, representing their very diverse condensation environments in their parent stars. As we can see, presolar grains are generally small. They are only micron to submicron in size, or even nanometer in size in the case of nanodiamonds. But our modern analytical techniques give us the capability to study their chemical, structural, and also asymptotic compositions, essentially down to atomic scale. And I'm sure this capability will keep growing with the rapid development of nanotechnology. So presolar grains can be identified in extraterrestrial materials from solar grains based on isotopic ratios, because different types of stars produce different nuclei by different nucleosynthetic processes. And we know the isotopic compositions of our own solar system, as shown here. The carbon, nitrogen, and oxygen are chosen to be shown here because they are the three most abundant elements in our solar system, except for hydrogen and helium. Now we zoom out of our solar system and look for dust grains from actual solar systems. So in these two plots, the solar system is represented by this red box. Here we go, we see that presolar grains are these things that look completely different from our own solar system. They show variations in the isotope ratios by orders of magnitude, which cannot be explained by any processes in our solar system. Also, we see here that we have both carbon-rich and oxygen-rich presolar grains that formed in different types of stars under different chemical environments, conditions. So far, we have learned where to look for presolar grains, but even in the most primitive meteorites like Murchison, presolar grains are extremely rare. The abundance of presolar silicon carbide, for example, is only 30 ppm. And this means we have to measure at least 1 million particles before finding only 30 presolar silicon carbide. So finding presolar grains in meteorites is pretty much like finding a needle in a haystack. So in order to improve the efficiency, we have some tricks. For example, for this acid-resistant feces, we can put this piece of meteorite in a mixture of a bunch of strong acids. In this case, most of the material will be dissolved away, and then we have acid residues that are mostly consisted of these presolar mineral feces. So this greatly reduces the time and the cost of finding presolar grains, and this technique is described as burning down the haystack to find the needle. However, the most abundant type of presolar minerals, silicates, are not resistant to acid dissolution. And in this case, we can't dissolve the haystack. We need to image the haystack to find the needle. And since such presolar grains are extremely small, they're only several hundred nanometers in size, so we need to conduct such isotope analysis at extremely high spatial resolution. Or else their isotopic anomalies would be diluted by the oxygen signals from the surrounding solar system oxygen-rich materials. So we have to use this instrument called the nanometer scale secondary ion mass spectrometer. So here in this image, we clearly see an extremely oxygen-17 enriched presolar silicate grain that is long believed to have originated from low-mass AGB stars. But recently, large magnesium-25 excesses are identified in such grains, which are inconsistent with low-mass AGB stellar model calculations, and this raises questions regarding their low-mass stellar origin. So more work is needed to understand where they came from, although this is not going to be our focus here today. So coming back to this slide, we see carbon-rich and oxygen-rich presolar grains are divided into different groups. And according to their population distributions, we also see the majority of the grains came from AGB stars. And for silicon carbide, this includes mainstream grains, Y grains with carbon isotope ratios higher than 100, and also Z grains here. This accounts for more than 90% of all presolar silicon carbide identified in extraterrestrial materials. And for oxides, this mainly oxygen-rich presolar grains, this mainly includes group 1 and group 2 grains. But as I mentioned earlier, large magnesium-25 excesses are identified in group 1 presolar silicates, and this raises questions regarding their long-believed AGB stellar origin. Here, I just want to briefly refresh your memory of AGB stars, and for the AGB experts here, you have to forgive me for this simplified picture. So AGB stands for asymptotic giant branch star branch, and this is a region in the HR diagram populated by evolved columnar stars, and this is a period of stellar evolution undertaken by all low and intermediate mass stars late in their lives. AGB stars have carbon and oxygen isotopic compositions different from the sun, as we saw in the previous slide, and this is because such stars are high enough for triple alpha reaction and single O cycles to take place. which results in their layered structure. They consist of a CO core, a helium burning shell, a helium layer, a hydrogen burning shell, and a convective hydrogen envelope. So current AGB stellar models predict that stars with masses around 1.5 to 3 solar masses can become carbon-rich in their stellar envelope during the AGB phase. And this is because of the occurrence of triple alpha reactions and the third dredge-up event, which can dredge up the hydrogen burning product to the stellar surface, so it can become carbon-enriched. Since silicon carbide is carbon-rich phase, so AGB stars of 1.5 to 3 solar masses are the parent star candidates because they have this carbon-rich environment in the stellar envelope for silicon carbide grains to condense. Then stars with masses below 1.5 and above 3 solar masses remain oxygen-rich during their AGB phase, and they have been proposed as the parent stars of Group 1 and Group 2 presolar oxygen-rich grains. These two plots further illustrate that indeed the majority of presolar silicon carbide and also presolar O-rich grains should have come from AGB stars because they're similar asymptotic compositions. We see mainstream grains have a carbon isotope ratio distribution similar to that of carbon stars. And this is consistent with the fact that AGB stars have been observed to be one of the most prolific dust producers in the universe. And in this talk, I will be focusing on presolar mainstream silicon carbide grains formed during the carbon-rich phase of AGB stars. So although these grouping schemes represent our best knowledge of the grain's stellar origins, I do want to point out that these schemes need to be taken with a grain of salt. This is because, for instance, in the case of AGB grains, the current AGB models, in fact, can't really explain the range of observed isotope ratios in AGB silicon carbide grains. And in the case of J-type stars, there's no well-developed stellar models, so we don't really know the range of isotope ratios expected for such stars, except for astronomical observations of such isotope ratios in J-type stars. So you may wonder, how robust are the classification schemes given here, and there another way, independent way to classify these grains. So to examine this problem, so in our recent study, we applied a machine learning algorithm to classify the grains based on their carbon, nitrogen, and silicon isotope ratios. So the algorithm defines a cluster by simultaneously searching for a group of grains with a Gaussian density distribution in this four-dimensional space. And as a result, what we see here is the mainstream grains in this region are mainly divided into 3 clusters. And those 3 clusters are divided and they are divided into 3 clusters because each cluster has a different range of silicon isotope ratios, which means that these 3 different groups of grains, mainstream silicon carbide grains, should have come from, probably should have come from AGB stars with different ranges of metallicities. Also, what we see here is if the algorithm points out that mainstream silicon carbide grains have a wide range of carbon isotope ratios ranging from 10 to 200, and this is different from the previous definition for silicon carbide grains, which mainstream silicon carbide grains, which was defined to have carbon isotope ratio below 100. So the previous definition is arbitrary. And because of this result, so in the following slides, when I discuss mainstream silicon carbide grains, I will include grains with a carbon isotope ratios above 100. Here, this plot represents the density distribution of mainstream silicon carbide grains in their silicon and carbon isotope ratios. Since AGB nucleosynthesis barely alters its parent star's initial silicon isotope abundances, so this silicon 29 ratio roughly represents the initial composition of a grain's parent star. And this delta notation is defined as the deviation of the isotope ratio from the solar system value magnified by a factor of 1,000. So in this delta notation, 0 represents the solar system value here. And because silicon 28 is a primary isotope and 29 is secondary, so this ratio roughly is expected to increase with galactic chemical evolution and therefore with stellar metallicity. So generally speaking, the higher the delta silicon 29 value, the higher the initial stellar metallicity. On the other hand, the x-axis, the carbon isotope ratio is affected by a number of processes, and we will discuss this in more details later. What we see here is that the grains define a very compact core in this distribution, and this core is in the class 9 identified by the algorithm. What it means is that this group of grains likely came from parent AGB stars with a restricted range of stellar masses and metallicities. In fact, this compact core is nicely explained by another piece of our recent work led by Sergio Cristallo. So in this work, Sergio coupled 40 AGB model yields with a galactic chemical evolution model and also a silicon carbide dust production model. And then the coupled model was able to calculate the contributions of AGB stars of different masses and metallicities to the silicon carbide reservoir in the solar system at the time of solar system formation. And if you're interested in the details, I encourage you to check out the paper, and I'm sure Sergio is happy to take any questions. What I want to highlight here is that the coupled model predicts that about half of the solar system silicon carbide grains should have come from parent AGB stars, about 2 solar metallicities with slightly two solar masses with slightly subsolar metallicities. And this predicted narrow mass metallicity distribution well explains this compact core observed in the grain data on the left. And the 2 solar mass AGB stars are predicted to be the dominant contributors because they were numerous at the time of solar system formation, and they are also predicted to dredge up more material than lower mass AGB stars. As I pointed out earlier, mainstream silicon carbide grains are classified as a group of grains from AGB stars based on their carbon, nitrogen, and silicon isotope ratios. But ironically, standard AGB model calculations provide a poor match to the grain's carbon, nitrogen, and silicon isotope ratios. Shown here is the same nitrogen versus carbon isotope plot as we saw earlier. So the literature Presolar silicon carbide grain data are shown as a density map here. And Sergio's fide model calculations for low mass AGB stars with the close to solar metallicities are plotted for comparison. with the current data. So a star, an AGB star, a low mass star starts with a terrestrial carbon and natrium isotopic composition, and first it becomes enriched in carbon-13 and natrium-14 in a stellar envelope because the hydrogen burning product is dredged up to the surface. Then during the AGB phase, the envelope becomes more and more enriched in carbon-12 because the helium burning product started to become dredged up to the stellar surface, and this results in increased carbon isotope ratios in the x-axis and also the carbon-rich environment in the stellar envelope. So compared to the models, because silicon carbide is a carbon-rich phase, so they're expected to condense in carbon-rich phase of the AGB stars. So we have to compare the grain data with the symbols given here. So as we can see, when compared to the 3D model calculations, the grains are more enriched in carbon-13 and nitrogen-15, and also the model prediction area is a pretty overlap with the grain data here. So this poor data model agreement was recognized a long time ago, and this was considered as the evidence for the occurrence of cool bottom processing. And here's a diagram for the CBP. So material taken from the envelope can be circulated slowly down into the radiative zone where it undergoes nuclear processing at enhanced stellar temperatures. And then the processed material returns to the envelope where it is rapidly mixed with the other envelope material. Since the envelope material contains a large quantity of hydrogen, so the consequence of this CBP is to allow proton capture reactions occurring at enhanced stellar temperatures to boost the AGB stars' production of carbon-13 and also nitrogen-14. And showing here is the are the CBP model calculations of Palmerini et al. 2011. As we can see, as we expected, the CBP models predict enhanced nitrogen-14 and carbon-13 productions for two solar metallicity AGB star, and this corresponds to increased nitrogen-14 ratio and carbon-12 ratios in this plot. And the two numbers given for each model calculation here represent the values adopted for the two CBP model parameters, the transport rate for the circulation and the maximum temperature encountered by the circulating material. Here we see that the addition of CBP to the standard 4D model calculations indeed can improve the match in the x-axis, but this results in an even worse match in the y-axis because the model predicts enhanced nitrogen-14 enrichment, but we need to enhance the nitrogen-15 production according to the green data shown here. So if this is an indication that the CBP is not the solution to the problem here, or that there's some problem with the grain data. So indeed, these presolar grains were buried in their host merchants and meteorite for billions of years. And we see in this carbon ion image that silicon carbide is surrounded by a large number of solar system carbon-rich particles, which are organics, and this means they're enriched in nitrogen. And we know Murchison experienced heating and also water-rock interactions on the parent asteroid. And these additional processes could introduce nitrogen from the surrounding organics into silicon carbide, which means silicon carbide the extracted silicon carbide grains could have become contaminated with nitrogen from the surrounding particles. Also, we need to conduct extensive laboratory work to extract silicon carbide grains from Murchison, during which terrestrial contamination could have been introduced. Oops. Here we go. Therefore, it raises the possibility that the lower the nitrogen isotope ratios observed in the grains could have been caused by different degrees of terrestrial and also asteroidal nitrogen contamination. And this consequently suggests that the grain's nitrogen isotopic composition may not truly reflect the stellar nucleosynthesis, and this raises the question regarding the classification scheme I showed you earlier, because it is essentially relies on the carbon, nitrogen, and silicon isotope ratios of presolar grains. And to investigate the possibility of contamination, so in our recent work, I applied 3 different approaches to maximally suppress contamination. So these light element isotope ratios of presolar grains are mainly obtained using this instrument called nanosims, as I showed you earlier. So it is an instrument to produce secondary ions by sputtering the surface of the solid sample using a primary ion source. And then the produced secondary ions can fly in the mass spectrometer following the electrical field and then get separated by mass by a magnet. Then isotopes of different masses can arrive at the detectors so that we can count the number of isotopes to calculate the isotope ratio for a sample. As we can see here, so in the case of this acid extracted silicon carbide, so it is coated with some organic contamination. So in order to remove such contamination during our analysis, so in the initial sputtering process, we implanted the cesium into the surface of the grain for an extended period of time so that the collisional process can remove such a surface contamination and expose clean interior grain surfaces before we start to collect our data. Also, because different elements have different electron affinities, we need to use 2 ion sources to produce both negative and positive ions. And in the past, the oxygen ion beam was much larger than the cesium beam, and this resulted in much worse spatial resolution when measuring isotopes like magnesium, aluminum isotopes. So in this study, we used a new generation of oxygen ion source, and its beam size is now comparable to that of the cesium source, as we can see by comparing the 2 images. They have comparable spatial resolutions here. As we will see, in the end of the beam sizes for both ion sources in this case are about 100 nanometer. And as we will see in the next slide, this greatly helps suppress magnesium and aluminum contaminations. And finally, we rastered the beam over each sample and obtained their ion images. And then the ion images can be further processed to produce an isotope image like this. And shown here is the case for reducing the initial aluminum-26 ratios for mainstream silicon carbide grain. The yellow contour line defines the silicon carbide grain, and we see this grain's ring is more enriched in aluminum compared to its core, while the core has a higher initial aluminum-26 ratio compared to the ring. So the inverse correlation seen here clearly points out that this ring represents solar terrestrial aluminum contamination. And thanks to the high spatial resolution achieved during our imaging data collection, so we can choose a smaller region of interest to exclude the aluminum contamination during our data reduction. And clearly in this way, by only including the counts from the center of the grain, so we were able to obtain a higher initial aluminum-26 ratio for this grain, and the reduced data is more representative of its parent star's nucleosynthetic signature. And here's the new result added onto the same nitrogen versus carbon isotope plot. And by comparing the new data with the literature data, we see greatly enhanced nitrogen isotope ratios. And the average shifts from 500 to an average around 3,000, almost a factor of 7 enhancement in the nitrogen isotope ratio. Now, by comparing the new data with fruity stellar model calculations, we see, in fact, the grains are enriched in carbon-13 and nitrogen-14 compared to model predictions. And then, by considering the occurrence of cool bottom processing occurring under these constrained conditions, so we can very well explain the grain data in the case of nitrogen and carbon isotope ratios. So the grain data can be explained by standard AJB nucleosynthesis and cool bottom processing during the AJB phase. In addition to carbon and nitrogen isotope ratios, the aluminum-26 ratio was also shown to be a sensitive probe of the CBP circulation temperature. And these two plots are from the paper of Palmerini et al. 2011. The left panel represents the CBP results for different isotope ratios by adopting a fixed circulation temperature with 3 different transport rates, while the right panel adopted a lower maximum circulation temperature with the same transport rates. By comparing the two panels, what we see here is that the carbon, nitrogen, and aluminum isotope ratios have different sensitivities to these two CBP model parameters. So the nitrogen isotope ratio is mostly sensitive to the transport rate, while the aluminum-26 ratio, this gray line here, are barely affected by adopting different transport rates, but is very sensitive to different maximum circulation temperature, while the carbon isotope ratios is sensitive to both parameters. So if we can obtain correlated aluminum-26 ratios in mainstream silicon carbide grains, this means we can provide a more stringent constraint on the CBP circulation temperature. So aluminum-26 is a short-lived nuclide with a half-life of 0.7 million years. And since presolar grains are even older than our solar system, they cannot contain live aluminum-26 now. And their initially incorporated aluminum-26 should have all decayed to magnesium-26. So we can measure the magnesium isotopic composition of presolar silicon carbide grains to infer the initial aluminum-26 ratio at the time of their formation in their parent stars. And here's a plot of their magnesium-26 isotope ratio versus their aluminum to magnesium elemental ratio. And the aluminum-26 ratio is normalized to the solar value. So 1 in the y-axis represents the solar value. So we see when the elemental ratio lies below 100, the grains barely show any aluminum-26 excesses. But when this ratio lies above 100, with increasing aluminum-27, the grains magnesium-26 excess also continues to increase. And this positive correlation clearly points out that the grains magnesium-26 excesses are caused by the decay of aluminum-26. And to calculate the grain's initial aluminum-26 ratios, we can simply subtract the true magnesium-26 from the total magnesium-26 count collected from the grain, and then the remaining magnesium-26 count for each grain represents the amount of magnesium-26 from the decay of aluminum-26. And finally, we can compare the literature data with the new data for their derived aluminum-26 ratios by using this histogram. And we see a factor of 2 increase in the derived aluminum-26 ratio. Aluminum-26 ratio in our study because of the suppressed aluminum-26 aluminum contamination, as I showed in the previous ion images. And then by comparing the same set of 30 model calculations with the grain data, we see the grains show a wider range of aluminum-26 ratios than the model predictions. Also, on average, the grain data are a factor of 2 lower than the AGB model predictions. This inconsistency cannot be explained by the occurrence of cobalt processing because CBP mainly allows more efficient operation of proton capture reactions, and this would increase the production of aluminum-26 instead of reducing its production. And this is the opposite of what we need here. So to reduce the AGB star's aluminum-26 production, it requires lower stellar temperatures or lower production of aluminum-26 due to uncertainties of the reaction rates, for example. Finally, we can make such a plot of nitrogen versus aluminum isotope ratios to provide independent constraints on the 2 CBP parameters, as shown by the shaded areas here. Overall, the grains grain data require CBP to occur at relatively low stellar temperatures to avoid efficient production of aluminum-26. So far, we have discussed cobalt processing based on a parameterized model of Pomerania et al. 2011 without considering the underlying mixing mechanism. So in this more recent work of Pomerania et al., the authors invoked that the plasma condition in a 1.5 solar mass solar megallicity star satisfy the criterion for the occurrence of magnetic buoyancy, so that deep mixing can occur in such a star to bring material from the convective envelope to the stellar interior for cobalt processing to occur. As a result, we see much enhanced carbon-13 aluminum-26 productions and also oxygen-18 destructions in these deep layers. Also, the magnetic buoyancy-induced instability is also needed by 40 stellar models to produce a suitable carbon-13 pocket in the helium intershell in order to explain the S-process isotopic signatures of mainstream grains. So quite promisingly, by fully including the magnetic buoyancy in 30 stellar models, the model calculations can provide a consistent explanation to both the light and heavy element isotopic compositions of mainstream silicon carbide grains. In other words, the grains carbon, nitrogen, aluminum, strontium, and barium isotopic compositions together can provide powerful constraints on model parameters when implementing magnetic fields in AGB stellar models. So in conclusion, Presolar grains are awesome. We can study bona fide stellar materials with the full battery of modern micro-analytical techniques to extract complete isotope information from a presolar grain of 100 nanometer in size. And the extracted isotope data provide valuable information about the different stellar mixing and nucleosynthesis processes in their parent stars. And with the improved techniques, we can obtain better isotope data to further improve our understanding of these processes, as I showed in my talk today. By suppressing nitrogen and aluminum and also magnesium contaminations, we were able to obtain cleaner isotope data that are more representative of the true stellar nucleosynthetic signatures. And by comparing fruity model calculations with the grain data, it points to the occurrence of cool bottom processing in grains parent stars. So in the future, I plan to work with Sergio, Sarah Palmerini, Marzio Busso to use the nitrogen and aluminum isotope data to further investigate the role of magnetic fields in causing the occurrence of CBP in AJB stars, and with both the light and heavy element isotope data of mainstream grains, we hope to draw a complete picture of magnetic field processes in low mass AJB stars. And I'll stop here. Thanks for your attention, and I'm